Welcome to part one of a 6-part series on precast concrete lifting. Precast concrete lifting is a massive part of the industry. There's so much variance in the elements that are manufactured, from concrete pipes lifted with an excavator to bridge girders lifted with a massive big crane on site, and units being shipped around like this one here that you can see. The temporary works that goes along with these elements is crazy, and it needs to be adhered to in your design. There's a lot of different elements and different ways of lifting concrete. So standard cranes in a factory to specialist cranes on site, and units being tilted. Like you can see these culverts, they come flat, they're lifted vertically. It's got to do with restrictions to transport as well. If culverts or units are very tall on a truck, they're not going to be able to be lifted off and the way that they should go in. Here you can see some tilting tables where walls are tilted very slowly. They're lifted vertically very easily, and they're handled and travelled across at very low speeds, so the demands on the unit will be low. That you would have to compare that to units being lifted with an excavator on site on a bumpy track, so it's different dynamics, different stresses that come on the units. But in a factory, as you can see, units are handled with extreme care. They're usually all 4 lifters are engaged equally, but not always. So there's a lot to think, a lot to design, and the standard brochures that are out there, are not good enough to design bespoke precast elements. So we thought, let's do this course to enable all of our viewers to be able to design precast concrete the way it should be designed, as manufactured. Many thanks, and hope you enjoy it.
So my name is Matt Collins. I'm the technical director here in Structural Innovate, and most of you probably know this already, that we primarily offer precast design and detailing services, extending from stadiums to bridges to car parks, culverts, tanks and tunnels. Anything precast we kind of can tackle. And as you know, precast units, they're manufactured at a factory, transported to site, and this requires the need for casting in of lifters in order to handle and install the precast units. This course is a culmination of all of our experience with precast lifting design, and our goal is to share the knowledge and help you understand what precast lifting design is all about. At the end of the course, you'll be in a position to be able to carry out your own designs. And again, as I said, we're always here if you need any further assistance. So on the previous slide, we also have a LinkedIn page. Our website is there, and we also maintain a presence on Instagram. Just all our latest projects and stuff like that. So you can take a look at those. So the course itself, as I mentioned at the start, so the course will be composed of 6 modules. So they're kind of each given a description here, delivered every Wednesday, 1 to 2 p.m. from now until the 20th of March. Each module is going to lead on from the previous one, building up the understanding. We'll have a quick recap. So like what everyone covered today, we'll have a quick recap next week just to kind of refresh your thoughts. And if you look at the list there, you can kind of see first one is introduction and lifting demands. Then we talk about capacities. Then we talk about kind of bespoke lifting, some worked examples, and kind of with lifting design, they're very I suppose useful to have a spreadsheet or something, because you might have repeatable designs that are just slightly different. So having a spreadsheet developed for that will greatly help your design office. So we'll give some hints and tips on how to maybe set up something with a nice kind of a flow to it. And at the end of each lecture, I said, we'll have questions and answers, but sometimes the lecture might run on. So whatever doesn't get covered, you can touch base with me if we don't have enough time for questions and answers. You can kind of hit me up in an email. So what's this module all about? So this is our introduction module. I've listed here the items that we're going to cover today. A lot of this may already be familiar to you, but the idea is to ensure that everyone understands the background of lifting design and has a good foundation for what is to come in the later modules. The introduction and administration aspects we covered already in the last couple of slides. And now we're going to move on to a brief history of lifters. So what types are there, different accessories. And again, look, most of you will all be quite familiar with all of these. So I'll try not to spend too long on them. Then we're going to get a bit technical. We're going to get into the latest codes and standards. So historically, they've been designed a certain way, but then there's codes out there to design them according to the Euro codes. So we'll dip into those and explain each part of it. And then finally, we're going to finish out the module by tackling how to calculate the demands on a lifter according to the latest codes. So that'll kind of give you one aspect of lifting design. So calculate your demands. Second aspect is design the capacities, which will come in the later modules. There's a number of kind of different, I suppose, aspects that need to be encountered when you're looking at the demands. So we'll cover each one and how it influences the design, and we'll look at some worked examples and questions and answers. So you can see here, these are, typical lifting inserts. So precast concrete, it's been in regular use since the 50s or so, and possibly a surge in the late 80s, 90s, and now precast has become one of the largest construction material sectors. So when it comes to lifting, traditionally, precast was lifted with slings, chains wrapped around the concrete, agricultural use for precast. And as the precast industry began to grow, move into building market, more architectural requirements, the need for cast-in concealed lifters was required. I suppose precast companies began to develop their own in-house cast-in lifting solutions, and these were manufactured in-house, often based on experience, casting in rebar, etc., or welded plate, or whatever they kind of could get their hands on at the time. But now all cast-in lifting products are provided by third-party companies. These are backed up by sound theoretical knowledge and testing, and this has standardized the precast lifting environment, so everyone kind of knows what a 5-ton lifter is. And it's very versatile. There are many types of lifters in use today, and I'm going to talk about the main ones. And firstly, the main cast-in lifters can be subdivided into two categories based on the type of head. So on the left here, we've got the lifting product range known as the spherical head lifters, or lifting pins, where there's a forged head for which a specially designed lifting clutch connects to the head of the lifter. You've got the rubber dome head that gets cast in around the head, and then the bottom foot plate is also kind of spherical, gets cast in, and the lifting clutch clips on. And on the right, we have the threaded socket, or the threaded socket, for which a male threaded lifting component is threaded into a female cast-in, like a coupler or the heads here, and the lifting eye that fits in here will attach to the crane. So in terms of lifting, with a lifting socket, typically be some additional component crimped onto the socket portion. So you can see here the different products. Mainly the wavy tail is one of the most common. It's a piece of bent rebar that's crimped onto the socket. There's even a spherical head here. We've got the flat plates. We've got the cross pin sockets. So all these will probably be very familiar to you. So how do these lifters actually transfer the load into the concrete, or vice versa? How does the concrete get all the way into the chains? So in terms of the lifting pins, the majority of these lifters also have a forged foot that gets cast into the concrete. The foot is the primary load transfer mechanism for the tension forces. So as the load comes on the pin, the foot bears against the concrete, and basically the bearing pressure then gets transferred in tension through the shaft of the lifting pin. When it comes to shear, particularly with the spherical head lifting pins, direct contact is made between the lifting clutch and the concrete via the form dome recess. So it's critical when dealing with shear, so when you're tilting panels or anything like that, that the lifting is carried out as per the manufacturer's recommendations. So the correct dome former needs to be used for the pin size, and during the lifting up, during the lifting, the orientation of the clutch needs to be such that the I suppose many people have different names for this, so that the clamp down pin is aligned with the angle of chains in order for it to work as per the manufacturer's recommendations. When we look at lifting sockets, so it's similar. So in terms of lifting sockets, such as the wavy tail shown here on the screen, the lifting eye is threaded into a socket that is cast into the concrete. And the waved rebar is the primary load transfer mechanism for the tension forces. So due to the waves in it, it forms a similar effect that it bears against the concrete, and the load is transferred in through tension up through the lifter. You'll notice that, or if you dug into the details, that all these types of wavy tail lifters, etc., they're all designed such that the rebar is the weakest component. So it makes design fairly simple. If you're dealing with a B16 bar that gets crimped onto the socket, you just have to design for the B16 bar. When we look at shear then, you can see that due to the swivel head lifting eye that gets connected in, there's a significant eccentricity between the application of the shear load, which will be at the top of the lifting eye here, and where it bears against the concrete. So this has an effect on the demands, basically resulting in moments being developed locally on the pin. But due to their design, this is eliminated as much as possible. But this is the primary reason, if anyone has ever gone through the brochures, behind the fact that without any additional reinforcement, socket lifters are typically limited to 12.5 degrees, whereas spherical head lifters are typically limited to 30 degrees to the vertical axis. And so it's critical that the lifting is carried out, again, as per the manufacturer's recommendations. Can't just swap out a pin for a socket without appreciation for the nuances for each. Correct lifting eyes, as I said, need to be used for the given socket size, and the lifting eyes need to be fully threaded into the socket so that the bottom of the lifting eye bears against concrete. There's no gap, essentially. So good quality control, clean out any concrete out of the socket before doing any of that. So here's just a snapshot of many different lifters that are used by a lot of precasters. Again, it's probably all bread and butter to you at this stage. You've seen every single one of these probably, and you've used them many times. So they're all used for different applications. For example, with slabs, we got the flat plate lifters, wavy tail lifters, probably more suited to wall panels, and similarly solid rod socket with the cross hole, or with the solid rod here. These ones here often used for, again, wall panels. This socket up here in the top right, into the face of the wall panel for attaching bracketry afterwards. So they all have their own unique applications for that. And then quick snapshot then of the actual lifting devices. So we've sampled here the devices that connect to the lifters, and on the left we have the lifting clutches that connect to the lifting pins. You got the solid steel one, or you got the wire rope version of it. And on the right hand side we have the same for the sockets, the swivel head lifting eye, and again the wire rope version of it. Again, many different precasters have many different preferences. Durability point of view, the solid steel ones are probably better. The wire rope ones could get damaged when they're used multiple times, stored incorrectly, etc. So again, everyone has their preferences. And then other examples of lifting. So straps can be used for lifting. Straps generally require a recess in the precast to ensure that the strap does not slide depending on the angle of lift. And then another common item is the spreader beam, which is shown in the image here on the right. Has the function of spreading the load uniformly to all 4 lifters in the slab. Again, this is required, has its uses. Very effective at balancing the load, and it can be used to develop more efficient designs. So the last, I suppose, lifting product that we're going to cover is rebar and strand lifters. So it's different to the castings in the way that the typical shapes and stuff that these types of castings take are different. You need different depths. It's a different design approach. So we have a separate module on this, but you can see here the typical shapes the top diagram here will be for rebar or solid bar, typically with 180 bends on it, and it can be orientated anyway within your unit. And then the bottom diagram is for strand. So strand, that bit more flexible, and you can't have as tight bending radiuses on it. You can bundle them together. You can use a steel sleeve then for the chain hook, basically, so that you don't crush any individual strand and that all strands work together. So again, we'll cover that in module 4, I think, basically these two products. Can be a useful alternative, and depending on what you're lifting, obviously, if it's a fairly architectural component that's going to be exposed, you may not have the ability to use something that projects out because it has to be cut off after and patched, but it has its uses. So that's the introduction to the lifting products, and we're going to get into the code now, and then before we get into the calculations. So a brief couple of slides here on the code. So there are two standards that are used in lifting design to the Eurocodes, and these are here on the left, EN 192-4, which is for the design of fastenings in concrete. This is a relatively general standard that covers all aspects of fastenings in concrete, including cast-in plates and channels, etc. There's a more specific standard then here on the right called CEN 15728, and that's dedicated specifically to precast lifting. There's a lot of similarities between these codes, and they cross-reference each other quite a bit. So in the scope, so section 1.1 of EN 192-4, there's reference to CEN 15728. So they make reference to the for lifting applications. And then when you look at CEN 15728, this should be your first port of call for your design formulas. However, it is limited in its scope and does then refer back to 192-4 for a lot of the reduction factors for the more non-typical scenarios. So the specific precast lifting code covers the very typical scenarios, and then for a lot of when you're dealing with edge distances, more complex forces and geometry, it kind of refers you back to the 192-4 for the first principles approach. Also, codes by their nature are very general, and these are just two other very good references that can be used in order to get a deeper understanding of the lifting design, and particularly the varying different failure modes and how they are determined. So we've got FIB Bulletin 58, Design of Anchorages in Concrete, and then this book here, Anchors in Concrete Construction by Eilighausen et al. So these are two very good references at filling those gaps when you're dealing with non-typical situations where a unit isn't a perfect rectangle. There's sloped surfaces, there's edges, there's voids nearby. When you're trying to just prove that your design is satisfactory, these are two good references to read up on and get that information. So, how do we design lifters? So there's two approaches. So the old way, which is the top half of this slide, in which the lifters were designed and still used today. So this is known as admissible load design or working load design. This approach uses global factor of safety applied to the resistance. So it calculates the capacity based on number of tests and then just divides by an appropriate safety factor. And this usually is in the range of 2.5 to 3, and based on historical testing. So this approach is well suited to the tabulated data in many of the brochures, and a lot of the brochures probably still use this approach. The Eurocode approach uses limit state design. Similar to designing concrete, designing steel is limit state design. So your ULS, your SLS, all that. So it recognized basically that a single factor of safety did not quite capture the intricacies of structural design, and hence separate factors of safety are applied to the loads, the resistances, and the materials of the varying different failure modes. So you can see here that at the end of the day, you still have the demand, which is E, has to be less than the resistance. So, and you can see here on the bottom right, where's my, there we go, on the bottom right. So the design demand, so the design effects, the load, are multiplied by their own partial factor, and then the resistances are divided by their own partial factor. So that will give you a safety factor on the resistance and a safety factor on the demand. And the safety factors then are for different reasons. So that's why they split them out instead of having a single safety factor. So looking at the Eurocode approach in a bit more detail, we start with the statement that the demand needs to be less than or equal to the capacity, or the design effects need to be less than or equal to the design resistances. So the design effects shown here in red is what we're going to focus on in this module. So basically how to calculate using this formula. So we'll expand out this formula for the different scenarios and how to calculate that. And then the capacities or design resistance is going to be the focus of the next 3 modules on how to basically work through this formula. There's a lot more going on in this formula when we break it down. So that's why we need that bit more time to go through it. So going back to the demand for precast lifting, the characteristic effect E is essentially the self-weight of the unit. So the self-weight is considered a permanent or dead load, and thus the partial safety factor according to the Eurocode on dead loads is 1.35, and that's according to EN 1990. However, the self-weight of a precast unit, we can determine it with a high degree of accuracy. Look, if it's a rectangular slab, it's volume by weight by unit weight, and we can, I suppose, determine the accuracy quite well. So there's an appendix in EN 190 that we can adopt. So Appendix B allows us to adopt reliability class 1. So that puts a factor of 0.9 on the load factor. Essentially, instead of having to apply 1.35, we only need to apply 1.2. So look, a little bit of saving, and every little helps, as there isn't too many more areas where we can save. I'll be adding on the load in the rest of the slides. So anywhere you can save is always a blessing. So when we talk about the demands, so on the previous slide we spoke about the partial factor applied to the demands, and we can see that the effects are a function of the self-weight of the unit. But we also have a number of influencing factors that we have to look at. So at the mold stage, we need to account for the type of mold and the adhesion of the precast to the mold. During lifting operations, whether it be in the factory or on site, the type of lifting machinery used will have an impact on the forces passed through the lifters. Then, like we talked about before, logic dictates that more lifters we have, the less load per lifter, so spreader beams or whatever to reduce the amount of load on the lifter. And then in most situations, it can be beneficial to use the spreader beam. So, and then also the last influencing factor is the angle upon which the chains are to the unit. So the steeper the angle, you're varying the proportions of tension and shear. So as you'll see in the capacities when we get to it, there are different ways of checking the tension loads and the shear loads, and the different effects on your design. Becomes very relevant when you're tilting wall panels, where they're all in shear at the start, and then as you tilt it, the proportions change from being all in shear to all in tension, and we'll go through that in the later modules. So I'm going to go into a little bit more detail now about all these, all these influencing factors. So when we are carrying out lifting operations, say for example in this case a simple slab, there are 2 scenarios that need to be considered, and hence we end up having 2 different values for the demand, and we basically calculate both and take the maximum result to compare against our capacity. So the first scenario we have is when the unit is still in the mold. So depending on the mold, the sides, etc., may or may not be stripped. So let's say, for example, in this case, they have been stripped, and thus the unit is now only in contact with the base of the mold. There's an adhesion between the concrete and the mold base, which needs to be broken in order to lift the unit. And you can see from the formula, I don't know why this keeps, there we go. We can see from the formula here that the demand, when you're trying to break the adhesion, it's a function of the weight of the unit plus the adhesion factor times the area of the formwork. So for a simple slab like this, the area of the formwork is simply the length by the width. And you can calculate that. Once the adhesion is broken, the unit is now free from the mold, but it now experiences dynamic effects from the lifting machinery. And this is accounted for here on the right-hand side by multiplying the self-weight by a dynamic factor and take the maximum value to use against your lifter capacity. So the instrument factors essentially are listed here again: type of formwork, dynamic coefficient, number of lifters, and angle of chains. For the type of formwork, okay, we mentioned there's factors to include your adhesion factor. Where do we get that information from? It comes back to CEN 15728. They provide a nice little table here to basically indicate what value you should take, with the most favorable value being asymmetrically pre-stressed elements. So that only needs a 0 to 0.6 kilonewtons per square meter. And when you think about it, pre-stressed elements, the pre-stressing is on the bottom of the unit, and therefore when the pre-stress is released, there's a kind of an uplift, a kind of a camber, essentially, that occurs and almost breaks the adhesion itself. But then when you're dealing with steel molds or even timber molds, you have a higher adhesion factor. So that'll get pumped in here into your equation, and you know all the other parameters, then you can calculate that value. The dynamic factors, again, like we showed in the formula, where we get that information, well, that comes from table 5 of CEN 15728. And again, nice little explanations here of, depending on the type of machinery you're using, obviously the larger, more stable machinery have lower dynamic factors, and then obviously the smaller machinery have higher dynamic factors. So they give kind of ranges here. We'd always recommend taking the upper end of the range. And on the next couple of slides, I have a few diagrams to help visualize what this table essentially represents. So the first line on the table, where we had a lifting coefficient of 1.2, you're typically dealing with tower cranes or gantry cranes in the factory, where they're quite stable elements. They move at a slower rate, and the unit therefore doesn't undergo as much dynamic forces. The next row was 1.4 for the lifting coefficient, and that's typically a mobile crane on site, or high-ab cranes. But the key thing that must be noted if you're using this is that the machinery must be stationary. So only the boom moves, and that is what is allowed you to use the 1.4 coefficient. If the machinery is moving as well as having the precast suspended, such as in this example, so we're traveling on even ground, so a concrete yard or level compacted site, use a value of between 2 and 2.5. Again, I'd always recommend using 2.5. And then, for example, when you have scenarios where the ground is uneven, so it's torn terrain, or a lot of excavation work is carried out, it's only actually been stripped back. Typically, a lot of enabling works for like civil works and installing culverts and ducts would, the ground may not necessarily be the most level, and therefore you can see that this has a lifting coefficient of 3 to 4. So this means that if your precast unit is 2.5 tons, the demands on the lifters are going to be over 10 tons. So it's to understand the full process, or the full amount of loads that your precast unit is going to experience is key to the design. So having an idea of how the units are going to be installed, etc., makes a big difference to the design. So that's the first two. So then When we talk about the number of lifters next, so we want to try and reduce the load on the lifters after having added on a factor of 4 for the dynamic. That's going to increase the demand. So now we want to try and see, can we bring that back a bit? And that's why if we put in more lifters, it's going to reduce the load. So logic dictates that we can divide the total demand by the number of lifters to get the demand per lifter. But this isn't entirely true, and there's a number of things you need to consider. Firstly, you have to center the lifters around the center of gravity to have uniform distribution. You can't have 3 lifters on one side and 1 lifter at the other and say each lifter takes a quarter of the load. If you have a beam or a wall with 2 lifters, one at each end, well, then you can say the lifter takes 50% of the load. If you say you have a circular chamber cover slab with 3 lifters in a triangular pattern around the center of gravity, then you can say the lifters take 33% of the load. However, if you have a rectangular slab with 4 lifters, similar to the left-hand image here, where all the chains go back to the same chain hook, you can't say that each lifter takes 25% of the load. In fact, in this scenario, some of the chains could be slack, and thus the effective numbers of lifters is said to be 2. Thus, any one lifter is designed for 50% of the load. So, big difference in 25% and 50%. You're doubling the load if you don't account for it. And the best way of describing this is to imagine a 3-legged stool with the weight applied in the center. It can be said that each leg takes about 33% of the load. However, if you have another leg is added, making a 4-legged stool, and the legs are not all the same length, there tends to be a wobble in the stool. I'm sure everyone has experienced this inside the pub or restaurant. So the point in this is when the stool is only balanced on 2 legs as it tries to transition from one set of 3 legs to the other. Hence, each lifter in a 4-lifter arrangement needs to be designed for 50% of the load. We can alleviate this with additional measures to engage all 4 lifters, ensuring that they take 25% of the load. And this is done by means of using the spreader beam here in the middle image. Or to be more general, what you're trying to do is you're trying to split the load in 2 at each connection point. So at the left-hand edge here, we've got the spreader beam splits in 2, and the right-hand edge splits in 2, and then those 2 loads all come back to the lifter hook. On the right-hand side, we have another option that's given in the code. There's 2 actual options here. One is where a chain goes around a ring, and the other where there's another kind of a bespoke item. Again, but the idea is to split the load in 2 all the time. The final one is the angle of chains. And for the angle of chains, we just do a bit of trigonometry. So if you had a spreader beam with the chains vertical, well then all the load is in tension. But as you create an angle to get back to the chain hook, a certain proportion of the load is going to be in shear. And this couple of formulas here, just basically simple trigonometry, that the force G, the weight of the unit, is essentially the force F up here experienced by the hook, and that has to be transferred through the pins. So in terms of the vertical loads, the tension loads, in this particular example with 2 lifters, the force in tension is half the force in the hook. A bit of trigonometry to get the force in the chain, and a bit more trigonometry to get the force in shear. So that will become a bit more clear when we go through the example. And yeah, so moving on to the example then. So that kind of covers all you need to know. A couple of formulas, a couple of tables, and that's all you need to know to calculate the demand. And that applies to all aspects of precast lifting, whether it's no matter what component you're using, whether it's rebar strand, whether it's lift and socket, the calculation of demands is always the same. So this is just a quick worked example that we have. It's a simple one, but it explains basically everything that we've just talked about. So just reading off the top there. So we want to calculate the demand per lifter in the factory of a precast concrete slab. The slab is 2 meters by 1.5 meters by 250 millimeters thick in an oil steel mold. There are 4 lifters, but only 2 are effective because we're saying it's only going back to the single chain hook. And then a forklift is used to demold in the factory and transport the unit across a concrete yard. So the angle of change is taken as 30 degrees. So that's the kind of information that you kind of have to gather in order to carry out the lifting design. And I've broken it up here into a series of steps. So it's always good breaking the problem down into a series of steps. Always have a good diagram explaining the values. So the first thing we're going to do is calculate the weight of the unit. Then we're going to basically dip back in and compile. We're going to pull out all the influence factors that we need. And again, there are 4 of them based on the information in the question at the top. And then we calculate the demand per lifter for adhesion. We calculate the demand per lifter for lifting and take the maximum demand and determine the tension and shear components. So a few nice small handy steps there. Step 1, calculate the weight of the unit. Take the unit weight. Concrete as 25 kilonewtons per meter cubed. It's always a good one to take. And the volume, it's all kind of simple mathematics from here on in. So 2000 by 1000 by 250 by 10 to the minus 9 to convert back to meters. And you get 0.75 cubic meters of concrete. And therefore, the weight of the unit, 0.75 cubic meters times 25 gives you 18.75 kilonewtons. So that's G, that's the dead load of the unit. And we will carry that going forward. So we have a bit of an explanation here then on the different influence factors. So the formwork in the problem was given as an oil steel mold with the sides stripped. So therefore the adhesion factor, if we go back to that table 4 from the code, that will tell us that for an oil steel mold, we use an adhesion factor of 1 kPa. And then the contact area of the formwork, we can calculate that. It's a flat slab on the bed with the sides stripped, so it's only the base that you need to account for. And that was 2 meters by 1.5 meters. So that's 3 square meters. And we'll use that in the formula on the next slide. When it comes to the dynamic lifting coefficient, the worked example is only for demolding in the factory. So it's assumed a forklift is used to demold. You might have other equipment. But again, we go back to table 5 of CEN 15728 and pick out the appropriate value. So it's a forklift unit on even terrain, and thus it was the 3rd row in that table, and that gives us a dynamic lifting coefficient of 2.5. Number of effective lifters is our next influencing factor, and since all 4 lifting chains are going back to the 1 crane hook, we can only say that 2 are assumed effective, and thus each lifter is designed for 50% of the total load. And then the final aspect was the chain angle, and the chain angle was given as 30 degrees, very common angle used in the factory, to the axis of the lifter. So it's always to the axis of the lifter. Sometimes your lifter might be in the side of the unit for tilting, and therefore the axis of the lifter will be horizontal, and you always take your angle in relation to the axis of the lifter. In the majority of cases, your axis of the lifter will be vertical, and therefore it's on the vertical axis. So it's 30 degrees to the vertical, not horizontal in this case. And then when we get to it, then we'll decompose that into its tension and shear components. So the next thing we need to do, step 3, is calculate the demand per lifter for adhesion. This formula was presented at the start, and we look at the components that we need the dead load, we need the adhesion factor, we need the mold area, we need the partial load factor, and the number of lifters effective. So we can compile all that. G was 18.75 kilonewtons, our adhesion factor was 1 kPa, our area of formwork was 3 meters squared, partial load factor that we discussed at the very start was 1.2, and the number of effective lifters that we just discussed was 2. Pump all those numbers into your formula and you get a value of 13.05 kilonewtons, so 1.3 ton to demand on the lifter to break the adhesion. Then, as we said, once the adhesion is broken, we need to calculate the demand due to dynamic actions. So there's a different formula for that. We've got the dynamic factor, the dead load, partial load factor, and number of effective lifters. Again, we compile all that here, with the only new item there being the dynamic factor for the forklift on even terrain was 2.5 kilonewtons. pump all that into your formula, and then you get a value of 28.1 kilonewtons. So a big jump, the main item being the dynamic factor. So the smoother machinery you use, the better, because you can see it greatly affects. So we over doubled. We went from 13.05 to 28.1. So it's over double the demand. And then the step 4, then we take the maximum demand from that. So the maximum of our two demand formulas, which is 28.1 kilonewtons, and going back then to the angle, which was 30 degrees, and the trigonometric formulas that we had. So if the demand per lifter is 28.1 in the vertical direction, so that's going to be our tension in the lifter, which is 28.1. A little bit of trigonometry then to get F1, which is the tension in the chain, and that's 28.1 divided by the cos of the angle, 30 degrees, gives you 32.4 kilonewtons, and the force in the shear direction, because we're at an angle, it's 32.4 multiplied by the sine of the angle, 30 degrees, 16.2. So summarize that then, and we're going to carry these values forward. So we're going to kind of keep this worked example with us all the way through, and we can see how all the other parts add to it. So in summary, we've got a tension demand of 32 kilonewtons in the chain. So that's what you have to rate your chain for. And then we've got a tension demand per lifter and a shear demand per lifter of 28.1 and 16.2. So these two values will be used to design the lifter itself. So as I said, we're going to use that going forward. So in this example, I've referenced all F1, but obviously F2, because it's all symmetrical, is going to be the exact same.
Excellent. Thank you very much, Matt. Great start. Thanks everyone. Thanks for everyone watching. Don't forget to check out lecture number 2, which will be uploaded next. And if you found this helpful, please like and subscribe, and we'll try and get some more videos like this up in the future. So again, as we said, this is part 1 of a 6-part series. Part 2 will come next, and please like, subscribe, comment, and hit the bell if you'd like to receive notifications when we upload videos. Thanks guys, cheers.